Okay, and okay, we can start now. Welcome to Geometry, Arithmetic, and Differential Equation of Periods. Today we have Pierre Vanhove, who is going to talk about Feynman integrals and period integrals. So Pierre, you can start.
Okay, so thank you very much for the invitation to talk in your seminar. Actually, as you know, I mean, we had some exchange some years ago when I was started to think about this kind of approach that you like to Feynman integrals, and I'm happy to report to you some progress we have been making with Chuck Doran, that is present online, and Andrei Novotseltsev, about actually trying to understand the relation between Feynman integrals, period integrals, and the differential equation that is satisfied. So, you know, I'm a physicist and the motivation comes from physics. So, I mean, there will be 2 slides on motivations from physics. So, Feynman integral, I mean, they come from, they are important in physics because, for example, if you look at a process that is two-body scattering, like two black holes here scattering, the physical process that you need to evaluate to get the signal that fits the gravitational wave signal, to evaluate that operation, you need to compute Feynman integrals. And these Feynman integrals are complicated multidimensional integrals, which are the basis, I mean, of every computation you can do in any quantum field theory. For example, this is the Higgs bump, the Higgs physics. This is some solid state physics, but they are extremely, highly transcendental function, as I will explain. But each time you get an explicit analytic expression for the Feynman integrals, then you win a lot of precision, theoretical precision, and then you can better try to fit your theory with the measured, the experiment, and compare the theory with the experimental measurement. So in a sense, I mean, it's a really important question that, physicists, have developed over the years many intuitions and many tools, but it's no, I think today, for a few time now, a mature mathematical problem. And the thing is that you essentially have, the question is that you have an object that is defined in some way by physics requirement, and there is some physics statement that then I will comment in a minute in a mathematical setup that says that at a given order...
Excuse me, Pierre, for interrupting you. I hope Hossein allows me to do this. So I'm a mathematician.
Yes.
And so whatever I heard about the Feynman integrals is that there are not integrals in any mathematical sense. So they are symbols, avatars, you call them whatever you like, but you cannot assign to them any accurate mathematical meaning, at least thus far.
Okay, so anyway, so the thing is that let me finish my sentence and then I answer your question. Is it okay? So the thing is that, so the point is that there's some statement about the fact that there exists a basis of function which allows you to, at a given order and perturbation, to compute any physical process. So, but what is this basis of function? What is the dimension of that basis? There are physics arguments saying that at each order it's finite, but we don't know what they are. So what are Feynman integrals? That's a very good question. So mathematically, for me, a Feynman integral is an integral of, you see, this is an integral in projective space. The domain, so this is the parametric representation. There are other definitions, but they are not actually needed for that talk. And so this object is this integral integrated over the positive quadrant. So in projective space, Pn minus 1, so you have n variables. They are all positive. And here you integrate a polynomial, homogeneous polynomial of degree L. So there is L. this is actually the order and perturbation, to some power here that I'm going to define in a minute. This power can be an integer or half integer. And here is another polynomial that is homogeneous of degree L plus 1. And here you see, because it's a projective space integral, I've been using a patch where xn equal 1. But of course, you can write it in terms of the natural differential form that you have on projective space, which I will use later in the slides. And here, the new i's are, a priori, for physics reasons, they are integer values, okay, positive or negative integers. So this integral is actually a well-defined quantity. It is in the class of the toric integral, for example, that you and I will mention that in the talk, that you meet when you look at the Gelfand-Zelevinsky-Kapranov type of considerations. And actually, the GZK formalism is very useful. It's a way to try to think about getting the D module of differential equations satisfied by this object. Okay, so you can take this as a definition. I have to tell you what are these polynomials and how they are associated with the graph. But at least, so this is an object, which, of course, you have to ask whether or not this is a convergent integral. And in general, so the little omega is the sum of all the value of little news. So suppose you take even all the news to be 1, so there is no factor here. So essentially, omega is n, the number of variables, minus L, that is a loop order, that is 1, 2, 3 is an integer, and D is the space-time dimension, okay? So D can be 2, 3, 4, okay? So we think we live in 4 dimensions. But then you realize that actually the gamma function can have a pole. So it can happen that when D is an integer, the omega becomes a negative integer, right? And as well, it could be that for values of D's at integer values, there is as well poles that are developed when you compute the x integrals. So essentially what's happening is that in this representation, you do an analytic continuation in the variable that's called D. And this integral has a pole expansion, which is, for example, if we think we're in 4 dimensions, so D around D minus 4. So there will be, for some integral depending on the loop on L, 1 over, for example, in 4 dimensions, it would be like 1 over D minus 4 squared times something plus D 1 over D minus 4 plus etc. So it's a Laurent series. And the residue...
So if I understand you correctly, so at this moment, this is a fairly classical integral, which, well, may have singularities, but there is no question of how you define it and how you extend it analytically. So there is nothing infinite dimensional in it.
So these functions are defined. So, okay. So you define it by analytic continuation in the space of the news and the D's. And the only singularities on hyperplanes in this space. So we all know, it's a study that already dates from the 70s, that we know that we can do this, what I described, this analytic continuation respect, for example, to around D being an integer. It's a Laurent expansion and the coefficient, okay, the coefficient of the D minus, for example, 4, the residue of the poles and then the coefficient of the vanishing term, they are all finite quantities. The integral will converge. So it's a converging integral.
Pierre, maybe I reformulate Sergei's question. For the first time I saw Feynman integrals, they were our infinite dimensional spaces, which at the beginning they didn't make sense. And but these are well-defined one. What is the relation?
Okay. I'm sorry. Yes. Okay. So I'm sorry. I didn't get that point. So yes. So I think you are thinking about deriving the Feynman integral from the Lagrangian and using the variational principle on the space of fields. And of course, the space of fields that are the field that describe the object that you are scattering, so either the photon, the electron. So in a sense, I mean, the functional integral, so the path integral is in an infinite dimensional space. And you need to do some, you need to explain why actually the way you treat.
Yeah, I'm so sorry, but well, so you came to a different tribe, so maybe
Yes.
talking the language of this tribe. So what I read about the Feynman integrals is that you need indeed try to minimize the action of some Lagrangian
Yes.
in the field theory over a infinite dimensional space of different scenarios of say interaction between particles. And
Yes.
this infinite space is not just infinite dimensional in the smooth sense of this, but it eventually involves infinite number of birth and annihilation of particles, so that actually what you are integrating is a very, very non-trivial manifolds, and which carries no natural measure. So the
Yes. But this is
Raffles was the impossibility of you can probably explain what means the extremum, but you cannot explain what do you extremum of what is the real physical process.
I mean, okay, so you are describing the path integral over the field configurations, and I mean, as a physicist, we know what to do, right? So there's no question that we are doing it right. I agree that mathematically you maybe want to be very careful about the way you do the variation of the action, and then you derive the variation of the action with respect to the interaction, and then you extract the piece that you want to compute, that are the amplitude or the correlation functions. Okay. So, but this part of the computation is something that is like very at very early steps. So the thing is that if you really want to compute an explicit, okay, maybe I can show you a graph somewhere. Yeah, if you, for example, want to compute a particle that goes from there to there and has intermediate over particle, then there's a way to deal with this integration over this, the functional integration, that associate to a given order and perturbation an integral, a Feynman integral, according the rules that Feynman gave us to treat this, the variation of the Lagrangian, and deriving all the way you are contracting the field and making everything, I mean, a computation, a quantity that you want to compute. So the thing is that this is not the purpose of the talk. I mean, the purpose of the talk is to tell you that at the end of the day, what you have to compute is an integral of a projective space of this differential form, and explain actually what is the property of this differential form over the projective space, and explaining why this integral is really a Feynman integral, in the sense that what you have read and it's equivalent to it's not something I can do without a blackboard and in a few minutes. So the thing is that so the problem is to compute that integral with this say this differential form, yeah, and the form of the polynomial here that are involved is this. So there is. So I repeat. So this one is homogeneous of degree L. This one is homogeneous of degree L plus 1. So if you do the computation in your head, then you realize it is homogeneous of degree 0. So, okay. And essentially the idea is that this is going to be some period of some motif that I'm going to express that sits in the middle cohomology. Okay. But to get to that point, I mean, I need to explain you what I'm computing. So the label here, gamma, refers to a graph. Okay, so here this is called, I mean, this is the first and the second Simonzik polynomial associated to a graph. But so this F contains a piece that is exactly the guy that you have here, times a linear hyperplane. So this is something that is linear in the projective space variables times some positive coefficient. And then there's a piece that is here. And the structure, the generic structure of this guy is very simple. I mean, it's just an homogeneous polynomial of degree L in the variables, in your n variables, with coefficients that are either 0 and 1. There is no negative, it's 0 and 1. So this one is dictated by the topology of the graph in some way, but still, so you, I mean, I will show you later, I mean, how this one is computed. But so first you have something that there is no parameter. Yeah. Yeah. So there are parameters here in this hyperplane. Okay. And then there is this piece that is the V gamma that is again homogeneous of degree L plus 1. Okay. But the coefficient depend. So they are non-trivial coefficients. Okay. And the fact is that, so at the end of the day, your integral here is a function of these mass parameters that are linear in that piece, and all the variables that are here. Okay, so when these variables vary, you want to understand how the integral varies. And in particular, you want to understand what is the differential equation that the integral can satisfy when I vary these parameters and these parameters. Okay. So now, so as I said, it's important that the degree of f is one higher than the degree of u. So now, what I'm saying is that you can rewrite this integral. So here, to make the formula on the slide, I took all the news to be 1. So the formula, the same integral, you can write it as a residue. I mean, so this is the residue of this object on the locus where you have the vanishing locus of this guy, and as well possibly the vanishing locus of that guy. So there are configuration when actually for chosen. If you choose well the exponent, maybe this one doesn't appear or this one doesn't appear. But generally, you have both polynomials that come into the game of the understanding the nature of the Feynman integral. And the problem is that if you try to look at what are the singularities, okay, I'm going to explain that, but the singularities of this integral, so the singular locus, they are generally non-isolated singularities. And this is making the whole, analysis of the nature of the Feynman integral quite, complicated. But there was, many years ago, some Spencer Bloch, Helen Eno, and Dirk Kramer, they say that actually what you do have is that the Feynman integral is actually a period integral of this relative cohomology. So in a sense, so you are integrating over Pn, you are in Pn minus 1, okay? You have to remove the singular locus, okay, so that's normal. But the problem is that this integral, you want to integrate something on the positive quadrant, okay? And the positive quadrant is not a cycle because it has a boundary, and second, the vanishing, so these guys actually vanish. So there's a non-trivial intersection between the boundary of this guy and this vanishing locus. This is given by the coordinate, the coordinate hyperplane. Okay, so 1, 0, 0, 0, 1, 0, 0, etc. So what they said is that essentially you have to look at the relative cohomology. So you are away from when essentially you perform the blow up, and then you have the respect to the normal crossing divisor, and then you are just computing something that belongs to that space, a period corresponding to that space. And then you start seeing that this is getting like a non-completely trivial, because, for example, let me show you a drawing. For example, in a simple case where you have just P2, so this is, and then you will have a curve that is an elliptic curve that I will mention later in the talk. And you see the locus f equals 0 goes through this point here. So what you need to do is that essentially to follow their procedure is that you put some P1, little P1, so that then you can, in a sense, well define your integral as avoiding the singularities, and then you want to go back to that situation. So all this process is, with the strict transform, etc., is, I would say, in a sense, you know what you have to do, but it's not trivial to do. Okay. So to give you a sense of, so the statement is that the Feynman integrals are period of the relative cohomology, after this one that I described, after having done, the appropriate plot and the strict transform. No, because the integral varies with all these parameters, these ones and these ones. You expect, you are going to have a variation of mixed Hodge structure. So in a sense, everything is over on the complex number, or so essentially, so it's a problem of variation of mixed Hodge structure, and you expect that the integral satisfies some differential operator. So for me, L is a set of differential operators, the family of, the differential operator and the D module. But the important point is that it's non-zero. There's a non-trivial right-hand side. And the reason is essentially because you are interested in an integral that is integrated over something that is not a cycle. Okay? So there are two questions here. There's one question is to understand this part. Then the second question is to understand that part, which has to do with extensions. And the third question is to understand the solution of this. So already deriving the minimal set of differential operator is something non-trivial, because, in a sense, when you look at the integral, it can be very deceiving on what you expect in terms of the underlying geometry that really controls this variation of mixed Hodge structures. And in particular, the fact that it has non-isolated singularities make your life, very, very miserable. So now, physicists have been trying to tackle this problem, and they have some, very practical way to do it. But at some point, it gets very costly computer-wise, and you clearly need to improve on the method and as well get a deeper understanding of what's going on. Okay. So in a sense, it's a place, as I said, that where you have really a map between things that come from physics and things that come from math, and in particular Riemann-Hilbert problems, which essentially you want to compute period, you want to understand the local monodromies, which you can do by an unitarity and understanding what physicists call unitarity of the scattering matrix. You can try to understand what is the complete system of differential equation. So what is the Gauss-Manin connection associated to that, which is related to what the physicists do when they do the integration by part method, and they write some first order system, and then whether or not it's the minimal one or not, it's a question, but at least they have a way to produce something. And then, of course, there's a question of what are the functions that you get when you compute this period integral. So, there's an infinite class of integral that gives you polylog or multiple polylogs, but there is as well an infinite class that gives you elliptic multiple polylogs, and then there is something beyond. And so whether you have period associated, you have to get period associated to Calabi-Yau only, or do you have period associated to abelian variety? So this is still an open question. But it's a question that I think is mathematically well posed as soon as you have the starting point that I'm using. So to get a sense of what's going on, I mean, I think it's useful to try to think in terms of the GZK approach, where you essentially have an integral that is a toric integral, which is, so this form is really of the form I just described. I mean, it's the parametric form for a Feynman integral, okay? And so then GZK tells you, okay, so there is this lattice, and then there is the differential operator, then there is this over differential operator that includes as well the Euler operator for the homogeneity in the integral, the cycles, and then there are some specific solutions that are the hypergeometric function solution, okay? So what's happening, and this is already something interesting, is that if you take this integral, I mean, actually, even you take the generic one, but you change the domain of integration. So instead of integrating over the positive quadrant, you decide to integrate over torus, okay? Then that changes everything, because this torus is a cycle. Okay, so you have to make sure that, of course, you avoid the singularities. I mean, so this differential form, as I explained, it has poles, right? So you make sure that you are manipulating something while you avoid the poles. Okay, so you have to do all the. But in a case where the integral is finite, you just take the same as before, but you just change the main integration to the torus, and then this is one of the periods of the geometry that is defined by the singular locus. I still haven't told you what kind of geometry it is, and it is actually given by one of the GKZ or GZK system of differential equation. So in a sense, I mean, it's something that is that was already noticed by Gelfand himself long time ago. I mean, and Gelfand and Kapranov, and so they knew that actually what they were doing was, I mean, linked to actually evaluating the Feynman integrals in parametric representation. But as you know, I mean, there are many refinement that you need to do when you do this toric approach. Is that first, I mean, as I said, it's important for Feynman integrals that you get inhomogeneous differential equations, and here you don't. Okay, so and essentially the fact that it's non-zero for Feynman integrals has to do with the fact that there are relative periods. So you have to extend that to relative periods. Okay, so that's possible to do, but as well the construction for those that are familiar to that, but this is summarized actually in that line, is that what dictate the nature of these differential operators are just the powers of a monomial. So the Newton polygon. So in a sense, the construction of these operators have to do with this lattice that is obtained by looking at all the monomials that you have in your polynomials here. But it's essentially agnostic to the actual coefficient. And in fact, you realize that the Feynman integral that you want, they are of that form. It's a toric polynomial, but you have non-trivial relations between the coefficients. So you have much less independent coefficient that you have in the toric case. So now this is for those who are familiar with this kind of period, the kind of considerations. They try to see where the problem is. So you get GKZ, for example, you get a D module. And then what happens is that you say, well, you know, my real problem is that I have less independent coefficients, so I want to impose restrictions. And I want to know what is my new D module once I have used all the relations between the coefficient in the monomials here. And that is in general a difficult question. I mean, so this reduction of the D module, I mean, so, and in fact, I mean, in a sense, it is a question of computing what is the minimal dimension of the annihilator of your actually differential form. And so this is one thing. And the second thing, as I said, is that you have to look at relative periods. And the why you have to look at relative period is what I said about the fact that the real integral you want to compute is not, I mean, a period integral in a strict sense. I mean, you have this domain of integration that is very specific. So in a sense, I mean, so there had been some recent analysis by actually the list of people there is a bit long to write up, but there is Albrecht Klem there, so which I mean Klem some time ago, you know, worked on that, but then he went back to some of the things that were motivated from mirror symmetry and Calabi-Yau's equation to this Feynman integral question, and then with a student and Claude Dur, they have some paper where they somewhat, in some specific case, I mean, revisit this question of the GKZ approach to some Feynman integrals. But there's still a lot to do. So, I mean, so the question is that, how do I find this guy? How do I find, okay, I call it the motif, but how do I find the variation of the mixed Hodge structure? How do I then understand each piece, I mean, including extensions? And how do I understand these differential equations? Okay. So, okay, I write it as if this is a theorem statement. So, Feynman integral R period. So, in all the cases that I will mention to you, you can prove it. I mean, since the argument by Bloch, Eno, and Kramer, I think are, I think a good, I mean, argument for that. So here the question is that there's a family of graph that is a nice family that is a two-point function. So where actually the degree of the f polynomial is n, and you are in projective space Pn minus 1. So that means the degree of f is so you have n variables and you have a homogeneous polynomial of degree n. And in fact, as we, as I will mention later, so the singular locus, which is f equals 0 in that case, defines a Calabi-Yau n minus 2-fold. So the first non-trivial case is when you have 3 lines, n equal 3, then you have a degree 3 homogeneous polynomial in P2, and that defines an elliptic curve. And the next one, okay, 3, etc. Then you have other cases that are more tricky. So here you see you have a homogeneous degree 3 object, the polynomial associated to that graph, in P4. So it's a cubic threefold, but I mean, there are a lot of singularities. So the point is that, in a sense, I mean, it's not a generic. So this is what I want to say. And it turns out that there's some elliptic curve behind that one. But you see how generic it's not, is that in general, when you will have an object that will be of two-loop type, two-loop means it has the homogeneous polynomial f that is in my integral will be of degree 3 in Pn, and n can be, so n can be 2, 3, 4, 5, etc., as much as you want. So there is a Feynman graph for that where you have here homogeneous polynomial of degree 3. This one was degree 2, where n the number of integration in projective space, you have as many variables as you want. And they are all part of the same kind of process at what we call two-loop order. So the thing is that you want to understand, okay, so for n equal 3, when you have the cubic in P2, okay, it's an elliptic curve, then what happens? I mean, is there at some point, I mean, when you have a cubic in Pn and n is large, I mean, is there something funny happening? I mean, what is the relation between, I mean, the structure of the graph polynomial and exactly the geometry that dictates the variation of a mixed structure? And the fact is that it's important to have, I mean, control of the singularities. So here, for example, there's an...
Still,
yes?
F comma depends on these physical parameters that
yes. So they depend on the physical parameter. So this is a function. Yeah, I'm just writing the projective space variables to tell you. So, for example, for this graph, you get a cubic in P5, but it's a singular one. So in a sense, it seems that the middle cohomology looks like a K3. I mean, but yeah, I mean, but the point is that because there are a lot of singularities, you can even lower the genius. You know, so this is so what I said is that if you take this F with generic parameters as you would do in a toric geometry, you will never get the optimal geometry. So, for example, I mean, okay, in some cases when you have a K3 surface, the toric case, when the parameter in the F polynomial is generic, you get a Picard number that is very small. Yes, and for the physical case, then you get a peak that is bigger. It has to do with the fact that because of the relations, I mean, then cycles disappear, and you know, it's like you really need to be able to be knowing what are the various cycles, the independent period associated to that singular surface. So, and this is a problem that is, I mean, difficult enough. So we have a conjecture with Chuck and Ray that actually. Well, okay, so that the Feynman integral satisfy a reducible function system, okay, that the ordinary differential equation are inhomogeneous differential equation whose homogeneous part is the Picard-Fuchs equation of a pencil of Calabi-Yau varieties. So, in a sense, I mean, you have to tell what kind of Calabi-Yau varieties you are getting, I mean, and how they are related to the various parameters I mentioned in the beginning of this integral. So the integral is in projective space Pn with degree of homogeneity given by L. So how n and L enter in the characterization of these Calabi-Yau varieties. And the thing is that one of the thing that is certainly the most surprising and actually was not obvious to me, and I learned all these things thanks to Chuck, is that actually you have to use the mirror description to really see what's going on. So in a sense, I mean, sometimes if you just look at the integral by itself, I mean, on a face value, you won't see really what is the geometry that controls the Hodge structure. So to make the talk a little more precise, I'm going to look at a special family of integrals, which is called the sunset. So some people call it sunset, sunrise, banana. So, but I mean, I am a romantic person. I like the sunset, and so I mean, so maybe some people prefer sunrise anyway. Whatever. So this integral, and I'm going to set myself in 2 dimensions. So the integral I want to discuss in details, because there are things where you can do things explicitly, and it already contains a lot of non-trivial geometry there. Is a case where the F polynomial has a form that is yeah, okay, so there is this guy that I call phi, yeah, and there's p squared minus phi. So you see phi is homogeneous degree 0, And because I have factored here the power of the integral, I mean the power of the coordinate, I'm getting this measure that is the natural, this is dx over x times an object that is p squared minus this Laurent polynomial. And integrating over the positive quadrant, okay? And that depends on the mass parameters here and p squared. And of course, you can understand that you can scale p squared away and then only have the ratio of the mass over p squared. So you only have really n independent parameters. But I prefer to write it this way for a reason that will come obvious. So when all this mass parameter are equal to 1, then what happens is that because of the symmetry of the polynomial to integrate, this integral becomes a pure period. I mean, actually, it seems that, as I said at the beginning, that this is not a cycle, but if you use all the symmetries of the integration, then actually you can remove the boundaries. And actually, so this quantity as a function of p squared times this, and is actually a pure period integral. And the pure period integrals, and this is the thing that is interesting, is that for values of p squared, Brothers numerically had, by numerical experimentation, found that this integral, where all the parameters are 1, and for special values of this p square, are given by L functions of L value in the critical band. And when n is large, you even found that these L functions come from moment of Klosterman sum over finite fields. So already you see that there is some non-trivial, so this is a way to tell you that Feynman integrals are starting to look like period. I mean, so far I've told you that as a fact. I didn't explain anything, but here, no, I'm showing you why people came to that. So when n equals 3, when p square equals 1, so that this is all the parameters are 1, this integral actually is just zeta of 2 times 1/2. When n equals 4, actually the vanishing locus, so f, so the denominator equals 0 defines K3 with pK rank 19, as we showed in a paper with Matt and Spencer. And actually the value at 1 is exactly the so there's the conductor. I mean, anyway. So there's the value of the L function of the K3 in the critical band at s equal to. It's in the critical band, and the FK3 is the associated with these modular forms of weight 4. So there's a lattice sum, and then there's a product of deducting eta functions. Okay. When n equals 5, then Brothers found that this integral evaluates to a number that is zeta 2 times another L functions, where the seed, I mean, the modular forms is now weight 4 level 6, that is given by this product of eta, deducting eta function square. And I mean, actually, it matches the computation that Veril did for the computation of the L function series associated to the cohomology, where X3 is the space that is associated with the vanishing locus of the denominator, the vanishing singular locus of the integral. Very good. So, but the thing is that I'm not just interested by the case where all the mass are 1. I'm just not interested by the case where the p square is 1. I want, a full function of the parameters. Okay, so since I just have an integral that is just 1 over something, so what are the singularities of this something? So for n equals 3, you have a cubic in P2, and actually defines a smooth elliptic curve. And isolate the singular point, which is so the vanishing locus of the Jacobian, which lies actually on the singular locus as well, is just x1 equal x2 equal x3 equal 0. That's easy. You're happy. It's everything works, it's smooth. I mean, so, but when already the next case, then the singular locus, you see, so the singular locus, you have 4 variables, so yeah. So x1 equal x2 equal x3, but any value of x4, and I mean, makes the, I mean, is on the, I mean, lies on the singularity of the Jacobian, or x1 equal x2 equal 0, and then this equation, this hyperplane. So you see, and the thing is that this singularity of the Jacobian, actually, they all lie on F. So as soon as you are on this configuration or on that configuration, F equals 0 as well. And then you see that because of, I mean, this, and so you have all the case with the permutation of the indices, of course, then you see that there are non-isolated singularities. Okay, so you can try, if you want, with your favorite program, compute the Milnor number, and then you would see that, okay, here the Milnor number is 8, and this one is, of course, I mean, it gives you that there are non-isolated singularities. So now what do I do? Because I want to compute, I mean, this is a very simple case, right? I mean, I just want to compute that integral here, right? So if I try to deform my polynomial so that I separate my singularities, then, you know, I lose. I mean, in a sense, I mean, then you can make something that you can manage with like a Griffiths-Dwork method or whatever, but then you pay a huge price in terms of efficiency, and then you have to remove your deformation parameter, then it's not the way to go. And as well, you haven't really understood the real geometry, which is what is the geometry of that integral? That integral is finite. So, okay, so what is really, if this is a period integral, so what kind of geometry, algebraic, I mean, that controls the nature of the Hodge structure? Okay, so one way to trick that problem of non-isolated singularities, since Griffiths-Dwork doesn't work, and as is, I mean, for me, one trick is to use the creative telescoping algorithm. So creative telescoping algorithm is a way to construct an object. So you have here your form. You take a set of parameters. So for example, you can take all the parameters of your integral, and you want to build a D-module of differential operator that kill your integral in this way. So in a sense, you want to have this differential operator to be a piece that doesn't depend on the projective on the integration variable, so the projective space variables, plus a piece that is a total derivative. So it would be like what you do in Griffiths-Dwork, like you do the reduction of the pole, and then you push everything to a D of an exact form in projective space. But I mean, in a sense, I mean, the idea is the same. So if you write it this way, this is the D of something, and here it's something, it's a piece of a differential operator that doesn't depend on the integration variable, so it gets out of the integral. Okay. So that means if you have achieved that, if you integrate over a cycle, then you can pull that one out. I mean, as long as the cycle doesn't depend on your physical parameters. But okay, for example, the case of the torus I showed you before was the case. And then the piece that is the dq here is a d beta. Then you integrate by part, and because it's a cycle, this one has no boundary, and then okay, and then you get 0. And this is one way, for example, to show that the integral, when I just changed the domain of integration, I kept the same integrand, but I changed the domain integration to the torus that I could construct, that you can construct with GZK, is actually as well killed because it's a period integral. But for the Feynman integral, you do that, and then you integrate by part, and then you eat the boundary contribution, and then you get an homogeneous term. So, so the logic is there. So the thing is that one way is to use this algorithm by Zaleyberg that has been then improved by many people like Frédéric Chizac and Christophe Couchan. And it's a way as well to derive, for example, the to try to do the GKZ type of approach and get the D modulo differential equations. And the algorithm actually is, in a sense, the reason why it goes over the non-isolated singularities case compare where Griffith's work can't do it because the reduction over the Jacobian LD doesn't work in that case, is because he makes some kind of ansatz of what is the structure of this rational function that you need in order to push away your poles. Okay, so to do the pole reduction. So instead of just playing with the Jacobian ideal, this algorithm makes some ansatz about the function that involves that, increases the degree, and at some point, I mean, you find the solution. So, I mean, in a lot of cases, this is working fine, but in some cases, at some point, I mean, it can be very costly. But the thing is that it always works for Feynman integrals, because for a reason that, I mean, I don't have the time to explain in that talk, is that you can prove that Feynman integrals are definite functions. So that means they are annihilated by a finite dimensional space of differential equations. And the fact that it's a definite function is a consequence of the structure that of the integrand. Okay. Morally speaking, I mean, since this is very close to GKZ, I mean, you know, this is by GKZ. I mean, this is already there exists a set of differential operator that act. I mean, annihilate your integral. GKZ is not going to give you the minimal one, but at least so you already know that there is some set of differential operator, that's minimal set, that is going to annihilate your integral. Computing this minimal set is not easy. I mean, even computing the dimension of that, it's a non-trivial computation. But okay, so this is why it's good to have an understanding of what is the geometry of the Feynman integral. Okay, so for the series of integral that I've been looking at, so this sunset family, where the graph polynomial is very nice, then the second semantic, so the pole of my integral, is actually a character of the adjoint representation of an. So that means the Newton polytope associated with that. So I mean, there's no pole. I mean, so if you expand everything, it's an homogeneous polynomial, right? So the Newton polytope of this guy, but if you write it this way, then you see you have shifted so that you see where the origin is reflexive with only the origin as an interior point. And the toric variety associated to that homogeneous polynomial, I mean, is the graph of the Kremer transformation, I mean, that you do when you act with the inversion of the coordinate. So for example, for the two-loop sunset, where if I expand everything, then this is maybe clearer. You know, it's an elliptic curve. You see, it's cubic. Nice. So this is actually the graph where you have here the coordinate hyperplane, and then you see that when x1 is 1, but x2 equals 0 and x3 equals 0, everything vanishes. So clearly, this elliptic curve goes through your coordinate hyperplane. So you have to do some blow up, and when you do the blow up, then you do the blow up at 3 points. So you have 3 p1s, and then you get this dp6. And actually, what I'm saying, the construction that you do here, with the fact that you have the root lattice of an and this the blow up, actually you have to do a recursive blow up, the blow up, I mean, you can do it for all n. So that means the n equal 3, n equal 4. So then that means when you increase the number of variables, then you just increase the number, the length of that guy, then the degrees. So that means then you can define, for example, the pencil of the ambient toric variety, which is defined this way. So this is my f equals 0. It's in the singular locus of my integral. And the fiber when p square equal infinity is the normal crossing divisor. Okay. And this guy, because it's equivalent to the anticanonical divisor of this toric variety, then we have a family of singular Calabi n minus twofold. So this is a case where actually the geometry of the singular locus gives you some Calabios in a simple way. So, and this one is, this one is not singular, it's an elliptic curve. It's smooth. But then at the higher orders, then it's not the case. Okay. Okay, so I'm sorry, my phone is ringing. So the okay, so switch it off. Okay, so then for this family, what you can do is that you can try to understand what is the relations between. How can you understand the full family of integrals that you have here? So in sense, the structure of this graph polynomial is so special that there's a complete intersection description. So this is birationally equivalent to this complete intersection description. So you see, it's very nice. Because you separate essentially the two factors that you have here, and then you see that there's a natural iterative construction. So the equation with n plus 1 is obtained by the equation from n by just a simple substitution. So you just add an extra variable this way, and you add an extra parameter this way. And in fact, geometrically, that means that there is a natural fibrations. So there's a fibrations, elliptic fibrations. So the family at the order n is obtained by an elliptic fibration that involves the family at the order n minus 1. So the case of the n equal 3, which is a starting point, for example, the case n equal 2 is not very, very interesting. So the case n equal 3, the vanishing locus is this elliptic curve, and what you get is that then you get a pencil of elliptic curve when p square varies, and when p square varies, the singularities are at p equals 0, p equals infinity, and at the position dictated by these parameters here. And you have an I2 fiber, an I6 fiber, and 4 I1s generically. And when all the parameters are the same, then there are collisions of fibers, and you get this. And because you have this understanding, then you can show that actually your Feynman integrals is computing, is a period of that Hodge structure with this twist, and actually it's an elliptic D-log. So it's a case where you can explicitly do everything. Everything works, it's smooth, and you can construct the motive. You can even explicitly obtain the expression of the Feynman integral from the understanding of your motive. The next case, which is the same equation with one more variable, it's a K-free surface. And this is where actually I said that things start to get interesting, because the generic case, if you take here the generic, so here you see you have 1, 2, 3, 4 parameters, okay, if you scale that one. But you have much more monomials. You have many more monomials, right? You have many more monomials than you have parameters. So if you just do a GKZ approach with arbitrary coefficient for all the monomials, you get K3, fine. but it has a picker rank that is much higher than much smaller. I'm sorry, than the one that you actually have, because I mean, in a sense, because the restriction of parameters, cycles go away. And one way to understand actually the geometry of that K3 is either by looking at it in the eyes. Okay, you can try to look at this, try to compute the set of independent periods, and try to look at the relations and try to see what is the transcendental lattice. You can try to do it numerically if you are powerful enough, and try to do some linear relations in the lattice, I mean, over the integers. Okay, fine, but you need to have a good control of the numerics, right? Or you can try to use what I said about these elliptic vibrations. So it's an elliptically fibered K3 with the picker rank that is given by this, and depending if the parameters are all different, we can prove, I mean, with Chuck and Andre, that I mean the fibers of the elliptic vibration are these, and depending on the way the parameters are selected, then the fiber type changes, and the picker rank goes up to 19 when all the parameters are the same. So this is a case where you see that it looks, I mean, the case when the mass are, I mean, 2 mass are equal, 3 mass are equal, I mean, it looks pretty much the same integral as before. So, and the change in the rank here, of course, is correlated with the change of the order of the differential equation, right? So in a sense, you know that when you're in a case when all the mass are equal, because of the picker rank, you are going to get a differential operator that is order 3, but when the picker rank is 16, it's going to be order 6, okay? And that indeed, we can construct the differential operator completely and see that indeed, when you do the specialization, you factorize linear piece, and then the operator factorizes the way you expect. So since the time, I mean, it's only, I'm almost finished. So now, oh, I see. So for the for loop case, then you get a pencil of Calabi-Yau threefold, and in fact, what happens is that you can try to you can compute the Hodge numbers, and you see that actually, I mean, there are various nodes, and the number of nodes changes when you start to specify the mass parameters. In the same way that here the number, the picker rank changed when you specify the parameter, then the number of nodes changes, and then of course the Hodge number changes accordingly. Up until the case where, I mentioned the numerical analysis by Broadhurst, where all the there's no parameter anymore because everything is fixed to 1. Then you get a rigid case, the Barth-Nieto quantique. So the thing is that in that case, by understanding the geometry there, because it's a Calabi-Yau threefold, then okay, then you expect that the minimal differential operator is order 12, and then each time you specify relations, then you jump the order by 2. So 12, 10, 8, 6, 4. And indeed, by explicit construction of the differential operator, we can see that factorization. So I'm going to finish on that. So in a sense, I mean, the point what I wanted to make in that talk is actually in relation to some discussion I had a long time ago with Hossein, when I was trying to understand how to get around this non-isolated singularity question. And trying to use some of the method he described on his website and in his book, but you see, actually, as you can see, even in the simpler case of a graph polynomial where the degree is correlated to the number of variables in projective space, I mean, already the geometry is non-trivial. I mean, it's very rich, and so, although the problem is mathematically well posed, I mean, in terms of understanding what kind of period you have, it's still a challenge to have a complete understanding of what is really a Feynman integral? Because now, if I tell you that I can understand the set of differential equations, I still haven't told you what is the integral, what kind of function this is. And so is this some kind of automorphic forms? Is this some kind of whatever? I mean, modular form associated to Calabi-Yos? I don't know. And it's an open question, but hopefully the consideration I described here maybe will help to refine that question and maybe lead to an answer at some point. So thank you.
Okay, thank you, Pierre. I think I first will stop recording and then go to